Hi, this is Peter with CalcBook, and today we'll be looking at a timber beam design and specifically looking at a truss joist Parallam PSL. So just a quick recap on our timber beam design, right? We are using the National Design Specification, also known as the NDS. And that has two books with it, the NDS Spec and the NDS Supplement. So the specification, right, that is your design procedures, your capacity equations, your general adjustment factors, that sort of thing, where you can design for flexure, shear, deflection, compression, and combined loading. And the supplement, right, that would typically give you your reference design values for any saw and lumber shapes, but for composite lumber, right, we do not use this. We use a manufacturer data table or information spec sheets from the specific manufacturer that you are going to be getting your composite lumber from. So for this specific example, we're going to be using the Weyerhaeuser truss joist catalog or products, right, and we're going to be using a Parallam PSL. So parallel strand lumber is what it's called. And so our problem statement for today, we are going to be looking at a header design or a beam design using the truss joist Parallam PSL. Our length is 16 feet. It is a fully braced beam on the compression side of the beam. We are dry conditions, so dry service, dry installation. Our width is 3.5 inches, and then we're going to be solving for the depth required for the loading. And our loading is 220 pounds per linear foot of dead load and 310 pounds per linear foot of live load. And we're going to be using ASD design method. So let's go ahead and open up CalcBook and we'll get started on the design. All right, we've got CalcBook open now. So we're going to click into our NDS 2018. Then we'll go ahead and click into our member design. And then we'll select Flexure design, strong axis, and shear design, strong axis. All right, so we've got that loaded up, so we can start to define some of our inputs here. The first thing we're going to have to do is change our component type. Right, we are going to be using a composite lumber, and since we are using a catalog shape from the Weyerhaeuser truss joist catalog, we are going to go ahead and click on catalog. And then you'll see the options come up from the catalog for Weyerhaeuser, and we are constantly adding to this, so just keep that updated. Or if you have suggestions or other catalogs you want us to include, just let us know. We can get that incorporated pretty quickly. So we'll go ahead and click on our 2.2E Parallam PSL. That's going to be our beam or header design. Our member width right is 3.5 inches, we said, and our depth we are going to basically define or solve for. So we'll leave it at 9.5 inches now, and then we'll come back and adjust as needed. The next thing we want to do is go ahead and switch over to ASD. So we'll toggle this over to the ASD method, click confirm. Our load duration factor, right, since we are going to be using live load, we'll go ahead and switch this to a 1.0. We said we had dry conditions, no temperature issues. This is not a repetitive member. And then our volume and wet service factor, leave those as 1. If you have questions on those values, talk directly with the manufacturer as they can provide you some guidance on that. So let's go ahead and go to our beam loading. Right, we have a 16-foot beam. We're going to want to analyze the shear at 0, or you could do 16, and then we'll do half distance for the moment and deflection. So we want to go ahead and add our dead load. So our dead load is a uniform load of 220 pounds per foot, so 0.22 kip per foot. And then we will add a live load of 0.310 kip per foot. All right, so we've got our loading all good to go here. We've got our self-weight included. We can go ahead and click over to D plus L so we can see our shear, flexure, and deflection graphs. And that all looks good. So let's go ahead and click over to our deflection tab. Right, so we have got our modification factor for long-term deflection, our creep factor, right, K sub CR. For composite lumber, right, we have a 1.5, so we can leave that as is. We are over quite a bit, but we'll come back to that once we've checked the rest of the designs. So let's go to our flexure design. Right, we said this is fully braced, so we'll go ahead and toggle that. Wet service factor, again, this is composite lumber is intended for dry installation, so if you do have questions about this, again, talk with the manufacturer. So we'll leave that as 1. We are over by about 35%, so let's kind of quickly step through here. So we are using the D plus L load combination. Right, we get our bending stress from doing M over S of about 3,900 psi. Then we can step through any adjustment factors we have, right? For this particular problem, we do not have any adjustment factors. They're all 1. For our beam stability, right, because it's fully braced, that's going to end up being 1 as well. So once we calculate all that, we can run through our adjusted bending strength about the strong axis, multiply all of everything together, and we get 20 to 100 psi, and that gives us a DC ratio of 1.35. And then for our shear, we are actually okay here. We could include check end bearing. We didn't specify that in the problem statement, but we could adjust that if we wanted to and add in our bearing length if we want to include that factor as well. Same thing again, right? We check our bearing stress, we check our shear stress, we go through our adjustment factors for each of those, and we get our capacities, and we have a 0.67 DCR for our shear stress and a 0.56 DCR for our bearing strength. So we are okay on both of those. So we really just have to deal with the flexure and the deflection. So let's go back to our general tab here. And there are specific depths for these members, typically from the manufacturer. So let's go up to 14 inches and see if that helps. So that's pretty good. I think there's one more lower. We could maybe try 11.25, 11 and a quarter inches. And that looks like that would work too. So let's just quickly check our deflection. And it looks like deflection is controlling here. So we need to upsize again to maybe back to that 14 and see if that works for us. We'll check back on the deflection. So that's good. We're down to a 0.69 DCR, and that makes all of our design checks within the acceptable range. So that is a CalcBook design for a Parallam PSL. We hope you enjoyed the video. If you have questions, please let us know in the comments below, and we'll see you next time.